Section 2.5 Continuity. When we plot function values generated in a laboratory or collected in the field, we often connect the plotted points with an unbroken curve to show what the function's values are likely to have been at the times that we did not measure. Let's look at the slide. Okay. These points were just what it is we collected the data. Suppose that we drop an object from a height of 80 meters, and then we measure the time elapsed when or how long it took for that object that has fallen from 80 meters to reach the ground. Like this. Suppose it's like that. Oh, whoa, oh no. Oh, I did not see that armadillo. So, poor armadillo. Let's do that again. So suppose we drop an object from a height of 80 meters and we measure the elapsed time it takes for this ball to reach the ground, and we collect those measurements only at Q1, Q2, Q3, and Q4. Okay, so suppose that it took 10 seconds to reach the ground, and what we did is we connected those plotted points with this unbroken curve, okay, to show that the function's value are likely to have been at the times we did not measure. So in doing so, we are assuming that we are working with this continuous function. So basically, what is a continuous function? If I were to draw a curve starting from A up to B, if I have a continuous function and I start to draw right here, as long as I do not lift my pen from this paper, or I guess from this slide, I have a continuous function from A to B. Let's look at the next slide and see what happens if we don't have a continuous function. Let's start again from A to B, and suppose I started right here. However, from this point, I continued on there. And because of that jump, this function is no longer continuous at this point. Say, call it C. Continuity at the point. Find the points at which the function f in figure 2.35 is continuous from 0 to 4, except at x equal to 1, 2, and 4. We have done this in class, but let me just reiterate what we did. Okay, the points at which f of x, our function f, is continuous are at x equal to 0, x equal to 3, and all the interior points from 0 to 4, excluding 1 and 2. Now, how do we know that the function is continuous in terms of limit? Okay, let's examine at x equal to 0. Notice that 0 is an endpoint. Let's call this a left endpoint. Right there, left endpoint. And so we will examine the one-sided limit. So we take the limit of f of x approaches 0, coming from the right. Here I have all my x's approaching 0, coming from the right. And where does my y approach? The y values approach 1. And it turns out that f of 0 is also equal to 1. What about at x equal to 3? X equal to 3 is an interior point between 0 and 4. If we check the limit of f of x as x approaches 3 from both sides, because it's an interior point, x approaching 3 from both sides, notice that all the y's are approaching 2. And in fact, what is f of 3? Well, we are lucky that it's also 2. And of course, any interior point between 0 and 4. Here, any interior point between 0 and 4, between 0 to 4. An interior point could be here, here, 3, okay, somewhere between 2 and 4, between 1 and 2, between 0 and 1. Based on x equal to 0 and at x equal to 3, here we say the limit of f of x as x approaches c will be f of c. So in other words, when we have a continuity at a point x equal to c, the limit exists and it's equal to the function value. On the other hand, if we want to find out where it is not continuous, let's look at these points where it's not continuous and find out why it is not continuous. At x equal to 1, what is the limit of f of x as x approaches 1? Well, we already discussed this in class and we said that the limit does not exist. Although we do have a function value, and here our f of 1 is 1. However, the limit does not exist. At x equal to 2, the limit of f as x approaches 2 is 1. However, what is f of 2? What is f of 2? It's 2. And they are not equal to each other. The limit of the function as x approaches 2 is 1, but f of 2 is 2. At x equal to 4, it does have a one-sided limit, the limit of f of x, as x approaches 4, coming from where? From the left, is 1. But, just like at x equal to 2, it is not equal to f of 4. f of 4 is 1/2. Well, of course, if we are outside the domain, then the function is not continuous anywhere outside, to the left of 0 and to the right of 4. So to define continuity from the previous slide and from the example, what we did is we examined the two endpoints of our domain as well as the interior. And notice that for this function f to have a continuity from the right, the limit exists and it's equal to the function point. At an interior point C, the limit exists as x approaches C because the y values from the left and from the right approaches f of c. And if we have a continuity from the left, the limit as x approaches b coming from the left is equal to f of b, y values approaching f of b. So we have, again, continuity at endpoints and continuity at an interior point. Definition. From our previous example, it's a function y equal to f of x is continuous at an interior point C of its domain if the limit of f of x as x approaches C from both sides is equal to f of c. Now, if we are at the endpoint, like this one, we have that the continuity is from the right if the limit of f of x as x approaches a coming from the right, the f of x approaches f of a. And it would be continuity from the left if the limit of f of x as x approaches b from the left is equal to f of b. So here I have x is approaching b from the left. My y values approaches f of b. Let's recap what we just said. A function f is right continuous. That means it's coming from the right at a point x equal to c in its domain if, again, the limit of f of x as x approaches c from where? From the right is equal to f of c. A function f is left continuous at a point x equal to c in its domain if the limit of f of x as x approaches c coming from where? The left is at the function value. Otherwise, what do we have? A function f is not continuous at a point c. We say it's discontinuous, or c is a point of discontinuity. Okay, look at this. We've got an example of a semicircle. And I think we did this in class, but let me go back and define our function. Okay, f of x is equal to the square root of 4 minus x squared. And by looking at the graph, what is the domain of f? The domain would be the closed interval from -2 to 2. And notice that if I were to trace, okay, suppose I were to trace the curve from -2 to 2 in the domain, look at how the curve behaves. I'm going through the curve and I don't lift my pen and it ends there back to 0. So what can we say about every point here? So if x equal to -2 is an endpoint, in particular it's a left endpoint, the limit of f of x as x approaches -2 coming from where? I'm coming from the right approaching -2, then it's equal to 0, which is in fact f of -2. Alright, what about the other endpoint? Let's look at the other endpoint. If x is equal to -2 and it is the right endpoint, okay, it's an endpoint, okay, well, what do we need to evaluate? The limit of f of x as x approaches 2. Where are we coming from when we're approaching 2 in its domain? We're coming from the left towards 2. So from the left towards 2, and it's equal to 0. And again, what is f of 2? It's 0. And of course, if I have the limit of f of x for any interior point, okay, let's pick out this c, and there is my f of c right there. So let's call that f of c. And what is the limit as x approaches c from both sides? Remember, if we're looking at an interior point, we have to find out whether the limit exists from both sides as x approaches c from both sides, and it's equal to f of c. In particular, what do you think is the value? Okay, well, all I'll do is just plug in and say it's 4 minus c squared. That is the limit of f of x as x approaches c at an interior point.